Hello, my name is Landon, and in this video we are going to be discussing Ksp, otherwise known as the Solubility Product Constant. So first of all, what is Ksp? As I just mentioned, Ksp is the Solubility Product Constant, which is also a value that represents the level at which a solute will dissolve into solution. Over here we have a visual representation of this. We have two arbitrary Ksp values, but here all we know is that this one's lower and this one is higher. In the case of the lower Ksp value, we see that there are more ions that are broken into solution or less ions that are broken into solution and more solid that has been left at the bottom. As for the solution with a high Ksp value, we've seen that all the solid has dissolved from off the bottom and is now broken into its key component parts in solution. So in order to understand how to calculate Ksp, we must first look at the general dissolution reaction, which is the general chemical equation that we use to determine how a solid or a salt is likely to break up into its key components in water. The water component we can assume is right here. So right here, this equation should look familiar. This is the KEQ equation, but specifically when we're talking about aqueous solutions, we instead use SP, solubility product, because this is more characteristic of using aqueous solutions. Before we can calculate Ksp, we first must look at the general dissolution reaction in order to understand the origin of Ksp. So the general dissolution reaction represents how we should expect a salt, in this case I'll say magnesium fluoride as an example, how we should expect this to break up into its key components in solution, and that solution is water. We can say that there's a little water right here which is not being shown in its liquid state. If we write this out, we should expect this to break up into magnesium 2+ in its aqueous form, plus 2 fluorine minus ions in its aqueous form. So this is how we should expect, in solution, magnesium fluoride to break up. Now, so why is this important? If we look back over here at the KEQ equation, this should look familiar. This right here is the KEQ equation of this reaction right here. Now, if we remember, we do not count solids inside the KEQ equation, since they are negligible. So if we get rid of solid, and because this right here is a reactant, remember products go on the top, reactants go on the bottom. We get rid of this, we are left with 1 here, and we are left with only the products inside the KEQ equation. Now, when this occurs, this is where we have the Ksp equation. So Ksp equals C, or big C, to the power of little c, and then big D to the power of little d, where big C represents the molar concentration and C represents the coefficient before the molar or before the compound. So in this case, little d would be 2. Okay, so let's move on to a simple Ksp problem. What is the Ksp equation for magnesium fluoride in its solid state when put in water and it breaks up into its 2 ions, magnesium 2+ plus 2 fluorine minus ions? So we need to remember from above that Ksp is equal to big C to the power of little c times big D to the power of little d. And this right here represents, remember, the Ksp or KEQ of an aqueous solution. Now from here, all we need to do is directly substitute the C values, these both big C's and little c's values, for the values that are in this equation right here. So all we have to do is assign either C or D to either one of these, doesn't really matter. So I'll do C for magnesium and then D for fluorine. This will therefore make the Ksp equation equal to magnesium 2+ to the power of its coefficient, which in this case is just 1, that hidden 1 there, times the fluorine ion to the power of its coefficient, which in this case is 2. So this right here is going to be the general Ksp equation for magnesium fluoride. Makes 2 plus manganese ions plus 2 fluorine minus ions. Now let's move on to a more complicated Ksp problem. So the value of Ksp of silver chloride is 1.8 times 10 to the negative 10th. What would be the molar concentration of silver and chlorine in pure water placed in contact with solid silver chloride? Okay, so first of all, I'm going to write out the Ksp equation that we just wrote above. So that'll be big C to the power of little c times big D to the power of little d. And now I'm going to just start off right off the bat with doing direct substitution. So we are going to put in the values that we know. So we do not know the value of C or D, but we know the symbol that we want to just put there to represent what we want to find in the end. So we will put on this side equals silver plus ions. You can see there's no coefficient in front of these, so that'll be it for that. And then Cl minus 2, these are both to the power of 1. And now we can see that the Ksp value is given. So the value of Ksp is going to be 1.8 times 10 to the negative 10th. Okay, so this right here is showing us what we want to find in the end, which is going to be either the value of this or the value of this. Since there are equal concentrations of both silver and chlorine, because of there's no coefficient in front of these ions, that means that if we find one, we find the other, because molarity refers to the amount of ions, not the element. It is not associated with the element type, only the amount. So in order to find this out, I'm going to write out this right here. So 1.8 times 10 to the negative 10th Ksp value is equal to x squared. So now you may be asking, where did the x squared come from? And that x squared came from, if you remember the ICE table, so the initial change and then equilibria, we have your silver chloride right there. We have our silver plus, and then our chlorine minus. And from here, we remember that solids are not counted in this, so we can just ignore that. And then we know that because it hasn't been placed in water yet, theoretically, the initial starting amount is going to be 0, and that will change by plus x on both sides. And then we have x, and we know that we will then condense these down to x squared. So that is where that x squared value comes from. So now all we need to do to find x is square root both sides. So that comes out to be 1.341, or 342, I'll do 3 significant figures, times 10 to the negative 5 equals x. So because x right here is representing both Ag and Cl, this right here will be the molar concentration of both Ag and Cl. That is it for this video. Thanks for watching.